All right, we move next to 2.4.2, motion along a line. We're going to see a lot of new vocabulary in this section, including displacement. We've already talked about average velocity, but we're going to kind of give it a new twist. We'll learn instantaneous velocity. We're going to talk about the meaning of the word speed and finally acceleration. And there will be some new rules here, and they're the free fall constants for planet Earth. So we begin like this in motion along a line. We want to suppose that an object is moving along a coordinate line, say for this case, an S-axis, so that we know its position S on that line as a function of time t. And we're going to call that function S. It's a function of time. So this is a term known as rectilinear motion. Rectilinear motion is when an object moves strictly forward and backwards, only in one dimension rather than two. Here's a Desmos graph to kind of illustrate what that means. See the purple dot at the origin, and I've defined an S function here as x cubed minus 7x squared plus 10x, and I've given the value of this point right now, well, it's 0, 0, but it will move to wherever the S function tells it to move, but stay on the x-axis. So we can kind of watch that purple dot move back and forth along a line, and it's that S-axis in this case. And you can see it actually changes position a couple of times. This is called rectilinear motion. So back to the notes. Displacement is a vocabulary term we want to become more familiar with. Displacement of an object over some time interval from t to t plus delta t is basically just the difference in the two positions. So delta s, in this case, the change in position, let's write that in here, change in position, is the position at the ending point minus the position at the beginning point. So then in rectilinear motion, we're going to define average velocity slightly different than what we have before. The average velocity is going to be the displacement over the travel time. In this case, that would be delta S over delta t. So how many seconds did you travel for, or how many minutes or how many hours did you travel for? The denominator kind of stays the same, but here we have our destination minus our beginning point, and that's the displacement of that object. So if that's the way we're going to define average velocity, then if we take a limit of it, now all of a sudden we're talking about instantaneous velocity. So if we take that limit as delta t shrinks to 0, then all of a sudden we have the velocity at a moment, not over an interval. And this is going to be called instantaneous velocity. And the key part here is that instantaneous velocity is the derivative of the position function. So when you see instantaneous velocity or just the word velocity, we mean derivative of position. So we may even see this called S or F prime of t or S prime of t, depending on if S or F was used as the position function. In our definition down here, velocity function v of t is the derivative with respect to time of S, the position function. So here's an example using those ideas. The figure to the right shows the time to distance graph of a race car. So essentially this is a position graph. We have time on the x-axis, and that is in seconds. We have S on the y-axis, that's the position, and it's measured in feet. So if we look at point P and compare it to point Q. So point P is the position of the car after 2 seconds. It seems to be around 50 feet. If we look at the position of the car after 5 seconds, it seems to be around 350 feet. We can take the average velocity from P to Q, and we see that written here to the left. The average velocity for the 3-second interval from time t equals 2 to t equals 5 seconds, which turns out to be about 100 feet per second. We can kind of see that here. the difference in the positions or the displacement, let's write that, this is displacement, is about 300. And then the elapsed time, 2 to 5, that's delta t, is 3 seconds. So about 300 divided by 3, about 100 feet per second. That's the slope of the secant line. But we also see a tangent line drawn in here at P, and that's your instantaneous velocity. And at 2 seconds, the slope of this tangent line appears to be about 57 feet per second, and that is a limit of the average velocity as delta t goes to 0. So we talked about a race car in the last example, and that might get you thinking about velocity versus speed. They're kind of the same thing, but velocity tells you a little bit more. Velocity tells you direction. So if velocity is positive, if v of t is positive, then you're moving forward or up. If the velocity is negative, then you're moving backward or down. So when an object is moving forward, s is increasing and velocity is positive. When an object's moving backward, s is decreasing, velocity is negative. So if velocity tells you a speed and a direction, if you take the absolute value of the speed, what you'll have, or the absolute value of the velocity, what you'll have left is the speed. So when you're driving your car and you look at the speedometer, that really is just speed. It's not just velocity, because you can drive your car in reverse and your speedometer will still move forward. But that's why it's called a speedometer and not a velocimeter or something like that. So let's move on to another example and let's read a velocity graph. A student walks in front of a motion detector that records her velocity at 1 second intervals for 36 seconds. So let's go over here to the graph and just label some things. This is time in seconds, and we know that it's 36 seconds. So over here to the far right is 36. This is 0, and let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are 4 second intervals. So 4, 8, 12, 16, 20, not 18, 20, 24, 28, 32, and 36. She stores the data in her graphing calculator and uses it to generate her time velocity graph as shown to the right. Describe her motion as a function of time by reading the velocity graph, and then we want to know when her speed is at a maximum. So that's the t-axis. The y-axis is velocity. So recall that velocity is the derivative of position. So this is giving us her speed and direction. When velocity is positive, remember we're moving forward. When velocity is negative, remember we're moving backward. Let's also take a look at the y-axis, or the v-axis, I guess, in this case. This graph goes from negative 7.5 to 7.5. So let's see, 1, 2, 3, 4. And then this would be 1, 2, 3, 4, 5, 6, 7. And these are negative. Okay, so let's talk about the motion that she is moving. So from time 0 to time, it looks like about 14. The velocity values are all positive. If velocity is positive, we know the direction is forward. So what we can say is she moves forward for about 14 seconds. Then from 14 seconds all the way until it looks to be about 26 seconds, so 14 to 26, so that's about 12 seconds, all of the velocity values are negative. So even though she's moving with some speed, the direction is backwards because these y values are negative. So then we're going to say she moves backward for 12 seconds. Now, watch what happens from time 26 to time 32. The function stays at 0. And so we're not moving forward. We're not moving backwards. We're actually standing still. So we're going to say that she stands still. Let's see, that's from 26 to 32, so for 6 seconds. And finally, from second 32 to second 36, the velocity values are positive again, so she moves forward for the last 4 seconds. All right, finally, when is her speed at a maximum? So remember that speed is absolute value of velocity. So without regard to the positive or negativeness of velocity, when does it reach its highest value? Seems to be down here, looks to be at about -7, but that happens at time equals, looks to be about 20. So speed is a maximum at time t equals 20 seconds. And even though this looks like a minimum on the graph, speed itself is a maximum because this is the largest absolute value of velocity. So we noticed in this last example that we had different speeds at different times, and that means that the speed is changing from one time to another. You may have also noticed on the purple dot on the Desmos graph that it moved at increasing or decreasing speeds as time moved on from 0 to 10. So that then brings us to thinking about the rate of change in the velocity. Well, the rate of change in velocity has a vocabulary term. It's called the acceleration. The acceleration measures how quickly the body picks up or loses speed. And what's even more important is that acceleration is the derivative of velocity. We're going to highlight that there. Acceleration is the derivative of velocity with respect to time. If a body's velocity at time t is v of t, then the body's acceleration is the derivative of v. So here we have a of t. It's the derivative of velocity with respect to time. It's also the second derivative of position, so d squared s over dt squared. So we may think of it like this. We have position, which is s of t. We'll go ahead and call that s of t. Then the derivative of that is velocity. So that would be s prime of t, which is v of t. And then the derivative of velocity is acceleration. And that would be the second derivative of position or the first derivative of velocity. And that we're going to call the a function, acceleration with respect to time. And we'll learn more about motion on a line in the next video.